Okay, great. So let us start. So in the vector calculus, so there is something called velocity and acceleration, which is an application velocity and acceleration. Now here, so you have to be aware of the position vector concept when we are dealing with the velocity or the acceleration. Now a position vector which represents a position of the particle in the coordinate axis. Right, so this is the only purpose of a position vector. So which represents the position of a particle in the Cartesian coordinate system or the polar coordinate system or whatever may be the coordinate system you can think of. Now let us say a particle is moving in this particular path. That means suppose if this is the standard coordinate axis x comma y, then this position vector is represented by a vector called r of t. So here x is changed with respect to time and y is also changed with respect to time. That means when this particle is moved from this location to this location, then correspondingly this is r1 of t and this is r2 of t. That means there are two different position vectors which were drawn and this change happened within a time of dt. So initially this location is x of t or x1 of t comma y1 of t, and the second position is x2 of t comma y2 of t. Right, so this is the position vector change. That means ideally the change that is happened in the radial direction is this is the change. So this is dr and the angle that is changed is d theta. Got it? So that's why a position vector is usually expressed as r is equal to xi plus yj, where x is a function of time in this case and y is also a function of time, right? So here a position vector can be a function of time or it may not be. If it is a static position, it is simply xi plus yj. But if it is varied with respect to time, let us say a particle is moving with respect to time, then it is a function of time. Got it? So this is xi plus yj, or this can also be expressed as r cap, or in short r bar. So both are one and the same. This is in polar form and this is in the Cartesian form. Got it? So this is in the Cartesian form. Got it? So this is the position vector. Now when we are dealing with the velocity and acceleration, velocity is nothing but is the rate of change of displacement or the rate of change of position vector. Position vector will give us the velocity vector. Got it? So this is v is equal to, in short, is nothing but dr is a function of time, dr by dt, where r is a vector and is a function of time. That means it's a vector. Got it? R is a vector which is dependent on the time. Here, and similarly the acceleration, so it is the rate of change of velocity is called acceleration. Is called acceleration. So this is A is a vector which is represented as dv by dt, where v is a function of time again. Got it? Or in other words, v is you can express as dr by dt, or d square r of t divided by dt square is again represents the acceleration itself. Got it? So here displacement is a vector and velocity is a vector and acceleration is also a vector. Clear? So note down this. So based on this understanding, so you can solve one problem, that is find the radial and transverse acceleration of a particle moving in a plane curve. Find the radial and transverse velocity and acceleration of a particle moving in a plane. So here actually, did you understood the problem statement? First of all, you have to be aware of this terminology of radial and transverse. What is radial? What is radial? Anybody aware? What is radial acceleration? Can somebody respond? Anybody is aware of radial acceleration and transverse acceleration? Okay, so nobody. Okay, let me explain. See this, suppose if the particle is moving in this particular manner, then if you draw a radius vector we mean it is starting from the origin going away from there. So this is whatever the direction which is coming out of your origin. So that is what we call as, this is the radial direction. So this is the radial direction. That means going away from the origin. That's what is treated as the radial. Now here, this is the direction of the radial. And the transverse acceleration is perpendicular to the radial. So that is how it is defined. That means this is the transverse acceleration. So this is the transverse direction. So this is the transverse direction. Now, other than this, actually there are two more directions we can think of. That is the tangential direction, which is nothing but tangential to the path. So this is tangential. So this is a tangential. And the normal direction, normal is perpendicular to the tangent. So this is the tangent. So this is normal direction. So like this actually, usually for a curve which is traveling, right? So you can think of, these are the standard methods of the directions. So radial and transverse, or the tangential and the normal. Tangential comes along the curve and normal comes perpendicular to the curve. But radial is independent of the curve, that is drawn from the origin to the curve. So this is the radial direction. So radial will continue in this direction. So this is the radial direction. And transverse is defined as perpendicular to the radial. Got it? Understood? Now? Any questions on this? Radial and transverse? Now actually he asked us to find out r and theta. Yeah, exactly. So radial direction and tangential direction is nothing but r direction in polar and tangent, so this is radial is r direction and theta is transverse direction. Got it? Okay. Now actually he asked us to find out the radial and transverse velocity and acceleration. So let the position vector of the particle be r. So r can be expressed as small r into r cap. Small r into r cap, where r is the magnitude, and r cap is the unit vector in the radial direction. So as I explained earlier, velocity is nothing but rate of change of displacement dr by dt. So this is d by dt of r into r cap. So r into r cap is r cap into dr by dt plus r into dr cap by dt. So r cap is the unit vector. Now let us see what is this r cap. R cap is nothing but a unit vector in the radial direction. So usually r is expressed as, so r cap you can express as cos theta I plus sin theta j. So this is how you can express the unit vector in the radial direction. How? Let us say if you take this particular position as, let us say this is r cos theta and r sin theta is the position in the polar form, right? So in the polar form, xi plus yj can be written as r cos theta into I plus r sin theta into j. So this is expressed as r with the unit vector cos theta I plus sin theta j, because the magnitude of this is 1, right? So mod r cap is equal to 1. So here r into r cap, where r cap equal to this one. Got it? This is how you can express r into r cap. Now dr cap by dt. So dr cap by dt is nothing but derivative of cos theta is minus sin theta and then plus into I. Derivative of sin theta is plus cos theta into j. So this is minus sin theta I plus cos theta j is dr cap by dt. Now as a random check, if you test the dot product of r cap dot dr cap by dt, can you find out the dot product of these two? Dr cap by dt is minus sin theta I plus cos theta j, sorry, into d theta by dt comes here, d theta by dt. What is the dot product of these two? Minus sin theta I plus cos theta j. It is coming out to be 0. That means this unit vector, so the magnitude of this is unit. So sin square theta plus cos square theta is coming out to be 1. So that means if I call this as the u vector or u cap, or actually I call this as theta cap to be specific. So this theta cap is perpendicular to r cap. That's what it is going to be proved. Correct or not? So r cap and theta cap. So r cap dot theta cap is coming out to be 0. Hence these two are perpendicular. Both are perpendicular. So if r cap represents the radial direction, theta cap represents the transverse direction, obviously, right? So dr cap by dt, in short, you can write as dr cap by dt is nothing but d theta by dt times of theta cap. So this is one fundamental relation. Dr cap by dt is equal to d theta by dt times of theta cap. So where theta cap is the transverse direction and r cap is the radial direction. So if you want to identify the radial component and the transverse component of the velocity, so r cap component dr by dt and dr cap by dt is coming out to be d theta by dt times of theta cap. Got it? So just note down till this point. I am going to erase it. Noted? Okay. So then this is r cap into dr by dt plus r into, so dr cap by dt is d theta by dt into theta cap. So this is the radial component of the velocity is dr by dt and transverse component of the velocity is r d theta by dt times theta cap, right? So r d theta by dt is nothing but the transverse component of the velocity. Got it? Understood? Radial component and transverse component, how we were able to calculate it. So that's why actually if you take it on the circular manner, so if you take actually a particle moving radially away, that means if the particle is moving along the radial direction, then there won't be any d theta by dt because theta is equal to constant. That means you have the velocity that is dr by dt. So this is actually in the normal +2 standard, whatever the velocity we calculate is just dr by dt. So you just take with respect to time a function and then as if like it is in the same direction, you will be doing the derivative. So this is also called as the rectal linear motion. But actually if the particle is moving in a circular fashion like this, then we say that the velocity or the linear velocity we call as r omega, where omega is the radial velocity, which is nothing but d theta by dt. So being r is constant for a circle, so this part will become 0 and r omega is the linear velocity which is traveling in the circular path. Got it? So r d theta by dt, in short we write as r omega. Got it? Okay. So note it down. Now, in the similar manner, let us find out what is the acceleration. So, r cap is equal to cos theta I plus sin theta j, and u or theta cap is nothing but derivative of cos theta is minus sin theta j sin theta I plus cos theta j. So this is theta cap, and dr cap by dt is equal to d theta by dt times theta cap, and velocity is coming out to be dr by dt into r cap plus r d theta by dt into theta cap. So this is the velocity. Got it? Okay. And then we'll find out the acceleration from the velocity. So this acceleration will come as, so dv by dt, a is equal to dv by dt. Now v is a vector represented by d by dt of, so this is dr by dt into r cap plus r into d theta by dt into theta cap. Now, if you take the derivative with respect to time, this A is equal to, so d square r by dt square into r cap plus dr by dt into dr cap by dt plus, so r d theta by dt into d theta cap by dt plus r into d square theta by dt square into theta cap plus dr by dt into d theta by dt into theta cap. So this is the derivative. So if you simplify this derivative further, d square r by dt square into r cap plus dr by dt into dr cap by dt is nothing but d theta by dt into theta cap plus r d theta by dt into d theta cap by dt. If I take the derivative of this, d theta cap by dt is equal to derivative of sin theta is cos theta. So minus cos theta I, derivative of cos theta is minus sin theta into j into d theta by dt. So this is coming as minus of r cap into d theta by dt, right? So d theta cap by dt you can write as, so minus d theta by dt into r cap plus r d square theta by dt square into theta cap plus dr by dt into d theta by dt into theta cap. Now, if I write the radial component d square r by dt square and then minus r d theta by dt whole square into r cap plus, so theta cap is dr by dt and d theta by dt here, and dr by dt and d theta by dt here, and here r d square theta by dt square, r d square theta by dt square plus 2 times of dr by dt into d theta by dt. So this is in the theta cap direction. So this is the radial and transverse acceleration. Got it? This is cap. Understood? Okay. Now here actually, if you understand carefully, let us think about the circular motion. So in case of circular motion, so just tie up a thread to a stone and then try to rotate in this particular format. Then the stone will continue to travel in a circular fashion. That means, let us assume if it is having a constant angular velocity, that means the rate of change of angle is equal to a constant value. So in such cases, now dr by dt will be how much? What is the rate of change of r value? That will be 0, right? So rate of change of r is nothing but 0 because the path of the travel is in a circular fashion like this. That means in this particular circle, the radius value is always maintained constant. That means from this particular point, this is the radius and there is no change in the value of r magnitude. Hence, here also it is r, here also it is r, here also it is r. So dr by dt is equal to 0 in case the circular motion. And assume that if it is a constant angular velocity also, the rate of change of angle change is coming out to be a constant. In such cases, omega is constant. Then rate of change of angular velocity, which is nothing but angular acceleration, will come out to be 0. Now, if you constitute all these points here, so d square r by dt square will come out to be 0 because dr by dt equal to 0. And here minus r times of this is d theta by dt is omega. So minus r omega square in the direction of r cap plus, and here d theta by dt is omega and d square theta by dt square will come out to be 0 because no angular acceleration we can think of. So we assume a constant angular velocity case. Now d square theta by dt square is equal to 0. And then dr by dt is anyway 0 plus 0. So in theta cap there is no acceleration. In the radial direction, that too in the negative radial direction, there will be a component of acceleration, that is r omega square, which is happening towards the center. So this is how actually it is happening. So this magnitude is r omega square. That's why we call this as the acceleration, the angular acceleration, right? So that is coming out to be minus r omega square. So though actually we are trying to rotate in a circular fashion, the acceleration direction is always towards the center. Did you notice that? The path of the travel is in a circular fashion, but the acceleration direction is towards the center. It is always tries to push towards the center. Got it? And that's what is the responsible component for the centripetal force in a circular fashion. Got it? If the particle is moving in a circular manner, so the centripetal acceleration is nothing but minus r omega square. So in case of constant angular velocity in a circle. Understood? Right, so this is one of the very important understanding. So because actually when we deal with the circular motion, right, in dynamics, right, so the way it happens is we will always think of the acceleration direction is always tangential to the path of the travel, but it may not be. So the direction of the acceleration may be different than that. So that is one of the best example is a circular fashion. So in the circular manner, if the particle is moving, the acceleration is not towards the periphery of the circle. It is always directed towards the center. So that's why if you push it, right, so the centripetal force that will try to drag your hand in the other direction. Got it? You are trying to bring it down. Got it? Okay, yeah. So any questions on this radial and transverse accelerations? Okay. So I think we are almost done with the syllabus except for the Serret and Freinet formulae, right? So you wanted anything you wanted me to repeat, or actually anything you have any doubts? So I think so maximum 1 or 2 classes will be done with this vector calculus, so that I am going to deal with the curves in space, which are nothing but the applications of Serret and Freinet. I think so the problems are pretty simple. Just to understand the concept, actually we have given this. So okay, so if you want to note down on problem, okay, note down this problem. A particle moves along the curve. So usually, right, so in case of this tangential, right, so what is happening is, so this is, if the particle is moving along this particular path, the velocity direction will be in this particular format, right? So this is v direction, correct or not? That is, the velocity direction is nothing but the tangential direction. So v is equal to dr by dt is a tangent. So this is a tangent, right? So that's why when you want to find out the velocity, so this is just dr by dt. Now you wanted to identify the component of the acceleration along the velocity direction is nothing but the tangential direction. You find out the unit vector in the direction of the velocity. So then find out the acceleration d square r by dt square and do your dot product with velocity unit vector. So this will give the tangential component. So this will give the tangential component. if you want to identify the normal component, then r minus, so a minus and the a tangential, this will be a normal. Got it? You will find out the vector, which is the tangent, so which is the acceleration vector, and then for the acceleration vector, find out a component of acceleration along the tangential direction. Then if you subtract the tangential component from the total acceleration, it is going to be the normal acceleration, because if this is the tangential acceleration and this is the normal acceleration, let us say if this is the acceleration, so you have calculated this product, that is the dot product with this one, and then this, if you subtract this one, then you are going to get this one. So this is the vector sum, which is coming out to be this one. Got it? So this is the normal component. This is an, this is a, and this is at. Got it? How to find out? Understood or not, Vishal? Now based on this understanding, let us solve one problem. You will get a fair idea on this. So tangential and normal are straightforward, because the velocity itself is the tangential direction, dr by dt. A particle moves along the curve r is equal to, a particle moves along the path of the curve. R is equal to t cube minus 4t. R is equal to t cube minus 4t I t square plus 4tj. T square plus 4tj. T square 8t square minus 3t cube k. So this is the position vector, where t denotes the time. Find the magnitude of acceleration along the tangent and normal at t is equal to. T denotes the time. Find the magnitude of acceleration along tangential and normal. Directions at t is equal to 2 seconds. Can you solve this one? This is straightforward. Find out the second derivative of r. So the first derivative of r is v is equal to dr by dt. And then substitute t is equal to, so this is v vector, you are going to get it. Now unit vector or unit tangential vector, this can be given as v bar by mod v bar. So this is unit tangential vector, I call this as t cap. And then find out dv by dt. So this is d square r by dt square, and find out at t is equal to 2 seconds. Then this what you are going to get as a. So a dot t cap is the tangential, a tangential, and then a minus a dot t cap. So this value is a normal. Find out this. What is the velocity at t is equal to? Eight I plus 8j minus 4k. That's correct. Everybody got the same? Right? Okay, great. So then actually find out the acceleration at t is equal to. What is the acceleration at t is equal to? Yeah, complete Nitya. Yeah, 12y plus 2j minus 20k. That's correct. So A vector and V vector both actually we have got. Now find out a unit normal vector along the velocity. So that is tangential vector. So what is t cap? 8i plus 8j minus 4k divided by square root of 64 plus 64 plus 16. So that is 12. So 8i plus 8j plus 8i plus 8j minus 4k divided by 12. So tangential vector t cap is equal to 8i plus 8j minus 4k divided by 12. So this is the t cap vector. Got it? And the tangential component of velocity magnitude is how much? 16. That's correct. Everybody got the same answer? Everybody got the same answer or not? So V vector we have got 8i plus 8j minus 4k. So this is V vector, and t cap is nothing but V bar divided by mod V. So this is coming as 8i plus 8j minus 4k divided by 12. So this is the tangential component, tangential vector or t cap. Now at is nothing but the a dot product with t cap. So this is the tangential component of the velocity. Now this tangential component of the acceleration. So a value we have calculated. This is 12y plus 2j minus 20k. 12y minus 2j plus 20k. So this is the acceleration, which is nothing but the total acceleration. So in the total acceleration, so tangential component will be 12y minus 2j plus 20k and dot product with the t cap. So t cap is 8i plus 8j minus 4k divided by 12. So I think this is coming as 16. Got it? Yeah, this is coming as 16. Now, if you want in the vector format, this is A tangential is nothing but 16 t cap. So this is 16 into vector form is 8i plus 8j minus 4k divided by 12. So this is tangential vector. At is nothing but a tangential vector. So this is the magnitude and this is the vector in total. Got it? Now, normal component of the velocity if you want, then subtract the tangential component from the total acceleration. So this is total acceleration is 12y minus 2j plus 20k minus, so 16 by 12 times of 8i plus 8j minus 4k. So this is the normal component of the acceleration in vector form. Can you simplify this and tell me? Four I minus 26j minus 44k. 1 by 3 times of 4i minus 26j minus 44k. So this is the normal component of the acceleration. So the modulus of this is 2 times of square root of 73, I think. Yeah. Got it? Do you have any questions on this? Any questions on this? So this is straightforward and simple. So velocity and acceleration. So only thing is, in case of finding out the tangential, so this radial and transverse acceleration, a little bit of confusion while taking the unit vectors. So that's why actually I have derived that. So based on that understanding, you will be able to find out the velocity and acceleration in the transverse and the radial directions. And in this particular case, this is the tangential acceleration and the normal component of the accelerations actually we found it. Now here try to memorize that formula, that is tangential and the radial component of the acceleration. Why? Because from vector calculus point of view, that may not be of much of importance, but this will be of having utmost importance when we are dealing with the dynamics. So there actually we will be dealing with the particles moving in the polar form only. So there actually the radial component and the transverse component of the acceleration, so you will be straight away using those formulas. Got it? Any questions on this? Okay, so with this I would like to stop the class for today. In the next class I am going to deal with the curves in space. So that is Serret and Freinet formulae. So I think so it may take 1 or 2 classes maximum to finish this. Yeah. So that's all for today. Yeah, thank you. Good night.